NASA's James Webb Space Telescope launched just 8 days ago. Right now, we are streaming the final stages of the Sunshield unfolding from the Mission Control Room in Baltimore, Maryland. This is live coverage of a real-time spaceflight operation as controllers prepare the James Webb Space Telescope for work. On the morning of December 25th, a massive rocket called an Ariane 5 lifted off from a state-of-the-art facility located in French Guiana. On board, the James Webb Space Telescope, bound for a point in space 1 million miles away. The process of preparing Webb for actual operations is called commissioning, and the majority of that work is taking place here at the Space Telescope Science Institute in Baltimore. What you're looking at now is some incredible footage, actually taken live from the James Webb Space Telescope during launch. And here we now see the Mission Operations Center in Baltimore. No worries.
And the emitter status is changed.
So I'm your host, Michelle Thaler, today, and this is really a momentous and historic event that you're looking at. We are actually going to be with you live as we finish the major unfolding of the James Webb Space Telescope Sunshield. This is something that has never been done in space before. This is a technology that's never been used in space before. I am really, really excited to be here. And I want to give you a little bit of a sense of what's going on here. A lot of things have been changing very rapidly. We have a beautiful set at Goddard Space Flight Center where we were going to give you a very well-rehearsed live broadcast. Because of the resurgence of COVID, we are no longer operating on that set. And so those of us who can be at home are at home for the protection and the health of our colleagues, and the people that absolutely need to be at the Mission Operations Center in Baltimore are there. That means that I'm doing this from my home and that you're looking at something that is also unrehearsed. This is a live event that we haven't really had a chance to put together in a very polished way. So as we do this, we're all in this together. I ask for your patience. If things are a little rough around the edges of this broadcast, that's the reason why. We also received a foot of snow yesterday here in Maryland where I live, so I'm having sporadic power outages. Hopefully we won't be worrying about that. But the reason we've decided to do this live is that this is something that everybody around the world is with us on. The James Webb Space Telescope is a true milestone for humanity. And it is a really historic, momentous day, and we want you with us on this day. So later in the broadcast, we'll be taking questions from social media. But to begin with, I want to begin discussions with somebody that's been with the Webb mission for quite a long time. And this is Keith Parrish. Keith Parrish, let's see, your title now is the spacecraft deployment engineer. Is that correct?
No. I'm the commissioning manager for Webb.
Commissioning manager. Thank you very much. The commissioning manager. Yeah, that's right.
Yeah.
So
good morning, Michelle.
Good morning. How are things in Baltimore?
Well, we're great right now. I'm upstairs from that operations center that you see there. So I'm one floor up from the operations engineers right now. Right.
Well, let's start about the people that are joining us. Perhaps some of the people that didn't see the actual live broadcast of the launch that we did. Let's talk about what's happened in the 8 days since the launch. So what's happened and what's going on right now?
Yeah, so we had an absolutely beautiful launch on Christmas morning. I think it was the best Christmas gift under the tree for a lot of people, including our operations team and all the folks that have been working on this for so many years. Right off the bat, we got a beautiful launch from Ariane, put us right where we wanted to be as far as our velocity. That evening, on Christmas evening, we actually did our first mid-course correction burn, and that was executed flawlessly. We actually used almost the minimal amount of fuel that we needed to do that. So, and that burn didn't happen by accident. That was years in planning. So just, big shout out to our flight dynamics team and our Delta V team and our propulsion and all of our teams. So they pulled that off flawlessly at exactly 12 and a half hours after launch. Then the next day we did some more turn on of activities. We got our antenna deployed. Eventually we got into getting our another burn a couple days later. We did a small mid-course correction. And then the next day, we actually started doing our deployment. So we deployed our forward and aft UPS shells. We deployed that big tower that gets the telescope up away from the spacecraft. And then the pace started really, really picking up. And it's been such a blur. I had to write down just to make sure I didn't forget it all. On about 5 days in, we actually did our roll-up covers, and those roll-up covers come in 3 stages. We release a bunch of pins that hold those covers to the shell. We released those. They rolled up in two out of the 3 stages, and we held them there. And then on New Year's Eve, we did what I would think was our most exciting deployment, and that's where we actually deployed our plus and minus booms, our J2 booms. And you can see some footage here of the real thing when we tested this on the ground for the last time. So everything you're seeing in that footage is what we're doing right now. But those plus and minus J2 booms came out on New Year's Eve. We had a great New Year's Eve here in the Mission Operations Center. And the big thing about those booms coming out is that's when we plunged our telescope in the darkness. For the first time, our telescope has no more sun on it, and it's been cooling as it should ever since. And then over the last couple of days, we took a little bit of a break over the weekend, as you've heard in the news there, which was much needed for our team because they were going like gangbusters for that week. And then yesterday morning, we started what we're doing right now, which is actually pulling in the corners and actually tensioning up the 5 layers of the Sunshield. So it's been an absolutely, just a whirlwind and a fantastic week since we've launched.
That's incredible. And so many congratulations. And I know that one of the things that's been sort of popular on the internet is we have a website actually where you can track where Webb is now. Can you give us a little bit of update? Right. So where exactly is Webb now?
I haven't checked it today. The last time I saw it, it was
right.
roughly about 500, maybe 600,000 miles from Earth. We're on our way to L2. One thing you'll notice on that website that I think we get a lot of questions on is that it looks like we're slowing down. And that's exactly right. Yeah. We should be slowing down. So we want to go out and sort of we want to be pretty much absolutely stopped when we get to that roughly 1 million miles away. And that's when we'll sort of be in our orbit around L2. So our velocity with respect to the Earth is actually coming down. You also see some temperatures on that page. That kind of gives a little bit of a feel. We have thousands of temperature monitors all around Webb. We try to pick some that give you a little bit of a flavor of what's happening on the hot side and what's happening on the cold side. And so far, everything is performing as it should from a temperature perspective. I think some other things you'll see on our website is where we are on our deployments. And you should be able to track that all on our website. So, huge shout out to our media team that does those websites and does everything you're doing today, because we're a fast moving thing and you guys are keeping up with us. So it's, kudos to you guys.
Yeah, we were talking a bit about some of the challenges with this, the resurgence of COVID has created. What's going on at the Mock and with your team to make sure people are safe? Tell me a bit about how you're dealing with the challenges right now.
Yeah, so like the rest of our nation right now, we're dealing with the surge right when we're doing all this. So we've known this. We've been in our rehearsal stage for a couple years now, since the reality of COVID hit the entire world. So we've started planning for dealing with COVID, a couple years back, and so we were ready for it. We weren't quite anticipating a surge like we just got right on top of our first week of the mission, but we have protocols in place to keep everybody safe. We do testing. We try to keep our numbers down. We do what we can practically, and then we do have cases. And our team handles that, and we keep those folks isolated. One of the things that has been a challenge is people who've worked a long time on this, and we had to isolate them. Now, fortunately, in this day and age, we can get them hooked up to our operations loop, and they can help us remotely from wherever they are. So we are handling it very well, but it's just another challenge that we just roll with it.
Well, let's talk a bit about what's going on today, because as we mentioned, there's something quite significant happening. So take us through, what's going to happen in the next, say, hour or so, and really what that means, what the significance of that is.
Yeah, so yesterday, we put out all these 5 layers of the Sunshield, and they're just kind of, they're not really tight. They're kind of, and then actually what we've been doing since yesterday is our Sunshield team, again, right downstairs right now. They're actually reeling in cables from each of the 6 pull points around the periphery of the Sunshield. So each one of those corners actually has 3 cables related to it. One cable actually pulls it really, really tight, and then 2 cables on that corner actually are lightly pulled, and they're connected to the periphery all around the perimeter of the Sunshield. And that's what gives us a very, very precise control over the shape of the edge. In addition to spreading the layers, we want to make sure that the layers are actually positioned correctly around the edge. So huge amount of engineering went into controlling those edges. So again, each corner has 3 cables, and again, we have 6 corners, so you can start doing the math on those. And all over, we have 90 different cables that have been reeled in over the last day. As we tension layer 1, we're reeling in 90 cables. As we tension layer 2, we're down to 72 cables. And today we're really only working with 18 cables. So we've gone from 90 cables, and today we're working with 36 cables for layer 4 right now. When we start layer 5 in a little bit, we'll be down to 18 cables. And we have motors that actually reel all those cables in. Very precise, very, very well, slowly done. Those motors turn. And then eventually we'll turn all those motors off, and we'll be fully tensioned. When we get into layer 5 here in a little bit, you'll notice that we actually go around the corners. We tension each corner up separately. So that's what's going on today, and we'll finish up here shortly.
That's absolutely wonderful. So, just to kind of talk a bit about this heat shield, give us a sense about how large this heat shield is, and what are the temperature differentials? I mean, how cold is it on the cold side versus the warm side?
Yeah, so we always throw around the tennis court analogy. I guess if you play tennis, you know exactly what we're talking about. If you don't play tennis, you're probably like, well, I think that's big. I don't know. Roughly, I'm gonna use feet here. I know. It's roughly 70 feet, 70 feet long, and about 54 feet wide. So you can see some dimensions there. Thank you for providing that in meters. So yeah, very, very large. It's one of the largest structures that has flown, that has been sort of robotically or automatically deployed. So yeah, quite large. Again, all the edge control, all the edge separation, and again, we're doing 5 of these. We're not just doing 1. So again, a huge shout out to our Sunshield team. They've been at this for many, many years, and you cannot overstate what an engineering accomplishment this is.
The thing that's so exciting about so many aspects of the Webb. Oh, I see here we've got a graphic about the
Here's some
temperatures.
temperatures. Yeah, so yeah, this is dramatic. Again, we try to put this out on our website, but roughly we get about, again, in Fahrenheit, we get about 100-degree Fahrenheit drop per layer. Overall, we get about 600 degrees between the hot side and what I call our coldest temperature on the observatory, which is our instrument detectors. Our instrument detectors are running right around minus 400 degrees. So you could boil water probably on the front side of us, and then on the back side of us, you're almost down to absolute zero.
So the huge size of this has to do with just the general size of this observatory, in total, and of course this idea that it had to actually be folded up to actually launch inside the Ariane 5 rocket. And I just want to take you back a little bit through that launch. I know that this was something that was an incredible day for all of us. I'm sorry, I'm getting yes, absolutely. I'm just getting instructions that we have a wonderful chance to talk to another person that's had, been truly a historic day, Jim Flynn from Northrop Grumman. And so Jim, please introduce yourself to us and tell us a bit about how you're doing today.
Yeah, I'm Jim. I'm the original Sunshield manager at Northrop Grumman, working in partnership with the NASA team. Have been involved in the Sunshield all the way from the original concept development, through the design, all the build and test, and through this final great phase of deployments on orbit.
So let's talk a bit about the Sunshield in details. I mean, for one thing, I mean, what an incredible story for you that you've been working on this for so long. Tell us a bit about what the Sunshield is made of. I also, let's start with the technical. I'd also like to, ask you some personal questions about some of the challenges you faced, some of the things you had to overcome. But let's describe this Sunshield. So to begin with, what is it made of?
So the layers are made out of Kapton E. It was made by DuPont, coated to get the correct optical properties for thermal performance. The bottom layer is 2 mils thick, that's 0.002 inches thick, and the other 4 layers are 1 mil thick, very, very thin material, but very, very strong when you're pulling on it. So it's very, very robust, in terms of the handling and the deployment. You have to be careful not to tear it or puncture it, but it's a very robust material. So basically, we make big, long rolls of this material, and then at our vendor that made the membranes for us at Nexolve in Huntsville, there's a very detailed process where we design, build, seam the gores together, and build the assembly that goes along with the big deployable structure system that you see here.
One of the things that I found really fascinating was how many of these actuators, these non-explosive actuators, have to work to get this thing to unfold. Could you describe a bit, what these actuators are and what has to happen?
So the majority of the actuators are really holding the folded Sunshield down to the structure. We need to make sure that it's in a nice, repeatable fashion from all the ground testing, keeping it all, in a controlled fashion, and then releasing it very sequentially so that we have a very controlled deployment. These actuators basically hold that down and electrically actuate and release the system, in a very controlled fashion that we test on the ground and we've shown multiple times is successful.
One of the questions I had, of course, is that when you're testing on the ground, you have to deal with the effect of gravity during your test. And now where Webb is, up in space on its way to L2, it's different. I mean, how do you simulate that in your tests? The lack of gravity.
Yeah, so we had to kind of break the test program into pieces. At the big assembly level, you really just can't do that. So we made subsystem articles. We would hang them almost in a shower curtain fashion, deploy them out, offloaded like you would see in zero gravity. So it's really a building up of a lot of different test articles in different orientations to show how it would perform in a zero-G environment. So you have to do it kind of in pieces rather than all at once with the final build.
And what were some of the major engineering challenges? I mean, can you, over your many years working on the Sunshield, what were some of the stories of, okay, at first we didn't know how to do this, and then we figured it out. What were some of the big things that stand out in your memory?
Yeah, I mean, originally it's we had an idea what this needed to look like, in its deployed state, but it was really, how do we take these 5 very thin membranes, fold them up and get them to fit within the payload fairing of the launch vehicle, and then be able to deploy it on orbit very reliably and, with a lot of confidence. So I think that's probably, in the big picture, just the ability to take these, 5 thin layers, fold them up, and then make sure that we know how we're going to deploy them to get to that final shape. That's probably the biggest challenge that we had, in the development of this subsystem.
I know that, whenever we've been talking about you, they've been saying, you've got to get Jim on this because he's the one that they feel was sort of the lead on this. I mean, the person that has been on it so long. How long have you been on this project? When did you start working on Webb?
It seems like my whole life now. I think probably maybe about 15, 16 years from beginning to end. So, so since the very beginning, since we were trying to figure out what the concepts were, building, maturing, and iterating along the way, and slowly improving the product and reducing the complexity, and then getting a very reliable system at the end.
Keith, is there anything you'd like to add to the story? I think you've been working with Jim for quite a while.
I mean, obviously, Jim is understating the challenges because he has overcome many along the way. So, the only thing I would say that people may not appreciate is the rocket launch itself and just getting the air out of all these layers. So, I'm sure Jim would like to add a little bit of detail there on how that was probably one of the biggest challenges.
Yeah, when you take the 5 layers and then you have to fold them and fold them again, you have to be careful about how that air is trapped in between the layers and how you can get it out in a controlled fashion. And that was definitely one of the biggest challenges, understanding what that environment was in the rocket, how quickly the air needs to evacuate the loads from basically this billowing inside the fairing. We ran a lot of tests. We built full-scale mock-ups in chambers that depressurized really quickly to verify the concepts. We had to design the system basically so that it was controlled through that depressurization environment and iterate several times in terms of making sure that that was a robust solution. So it was definitely one of the challenges, not just having it folded up and repeatedly getting it on orbit, but being able to vent that air that was trapped in between the layers in a controlled, reliable fashion so that the system basically could withstand those depressurization loads and deploy on orbit.
Yeah, what we're looking at here, the image that they have for us was that spectacular, real image of the observatory pulling away from the rocket. And this was one of these things that I could hardly believe was real when it was happening. It was an absolutely gorgeous shot. And
DEU stop deploy.
oh, sorry, I'm just hearing an instruction from the mock. I was wondering if that was right. Yes.
Yeah, so they finished the layer 4 forward tensioning. They'll move on to the aft, and layer 4 is almost complete. Will be complete after the next major move.
Yeah.
Just amazing. One of the questions we've been getting from social media is that we had that image of the observatory pulling away.
At 622.017, ready to go to DEU operate frame 10. The command line looks good. You're go to execute. Execute.
Okay, so I guess I've heard that Jim needs to go to the console. That we're coming up on the very end of this. So Jim, thank you so much for joining us, and congratulations on everything, and best of luck for the rest of today.
Yeah, I just wanted to congratulate the entire team. It's just been a hugely talented team from beginning to end on the Northrop NASA side. A lot of brilliant people working a lot of hours and really a lot of dedication to get us here to this point. And there's a lot of people out there that really deserve a lot of credit.
Yeah,
and,
I can confirm.
Kudos for the success that we're seeing here today.
Well, thank you so much for joining us.
All right, thank you.
At 622.019, we are ready to execute that. Clock looks good. You're good to execute.
Yeah.
So Keith, can you give us an idea? We're hearing these instructions coming over right now. What's happening at this very moment?
Yeah, so what you're hearing the voice of our DepOps lead, Nancy, and she's awesome, and she is coordinating between our flight operations team, which is actually sending commands up to the spacecraft, and she's sort of the liaison between that group of folks and actually our deployment engineers.
And OC, you are go to move the aft MTS motor pair.
Copy.
And what she did there, she just told them to send the command to start running the motor on the aft tensioning mechanism. And if you look at the OBT right there, if you can see, you'll see 3 layers. And
OC, you can queue up the DEU stop.
Roger.
You'll see the 4th layer rise here pretty soon.
And the motor status for the aft pair is moving.
And it's worth mentioning, you used an acronym, but this is actually a real-time animation that, although we can't see what's going on with the observatory, this is actually showing you what configuration it's in at the moment. It's based on the data.
And that brings up a good point. I know folks have been interested in, why don't we have cameras? Nobody would love to see Webb doing its thing right now than us. So it's, one of the things we really did want to put cameras on Webb. However, Webb changes shape a lot. You can tell over its deployment. It's going through multiple different configurations. So we just didn't need one camera. We would need multiple cameras in multiple locations. The other thing about Webb is it's very, very shiny on one side, and it's incredibly dark on the other side by design. And so we would have to take artificial lighting. Ultimately, we wanted cameras, but the engineering usefulness of those cameras just wasn't there unless it got really, really complex fast. The other thing is our cold side is really cold. So any camera on that side would have to be designed almost from the ground up to survive on that side. It would fall apart if not, and we'd have debris floating around. Possibly, it would, unless we started from scratch. So, and then the other thing, we're trying to keep our heat loads on that side very, very low. So all those things kind of combine together to say we really want these, but we just can't do it. So maybe from scratch, from day one, if we started over again, we could implement them in. So all that being said, we take all of our telemetry that's coming down from Webb. That's actually the numbers that we see on our screens and all the different information. Webb is incredibly instrumented. It's telling us everything about itself at all times, its position, where all these deployments are. But we take all that data and we synthesize it into a visual tool, which we're seeing on the screen right now. And we don't use it from an engineering perspective as far as this is what's really happening. The numbers tell us what's really happening. But our incredible OVT, our observatory visualization tool, they put a very good cool tool together, and this kind of gives us a little connection to Webb, even though we can't see it. This gives us that visual and spatial recognition of what's going on, and it's been very useful to our engineers as we work through different things that have been going on.
Wonderful. So, Keith, do you have any idea, are we sort of at a countdown about how much time it'll be until we know that this is completed?
Let's see, you should be doing layer 4 on the aft right now. That's quite a long motor move for this. So, and I always pull up here, I'm listening to a bunch of different operational loops. But they have got that started, so we should see that going right now. And again, right now on the app. Yeah, go ahead, Michelle.
Oh no, please go ahead, Keith.
No, I was just going to reiterate that we have 2 corners there. You can see in that view of the OVT, there's actually 2 corners. So we actually have 2 sets of mechanisms winding 2 sets of cables for each of those corners right now. You can see up in the corner there, maybe you can see in the corner, you'll see some of that data that's coming down from Webb that's counting up. Those are our instrumentation that tells us our position of our motors and how many, how our motors are turning and how fast.
I think that we have a few minutes here to maybe go back into some of the explanation as to why this heat shield is required. The whole idea about infrared astronomy and why it's so imperative to keep this particular observatory so cold. So maybe I'll just start by a bit of background about the infrared. And infrared astronomy is something that I've been involved in since I was right out of my PhD. I started working at the Jet Propulsion Laboratory in Caltech on the Spitzer mission a long time ago. Infrared radiation is something that we commonly think of as heat radiation. And infrared, the actual word infrared means beyond red. So this is a color that our eyes don't see. Our eyes are only sensitive to a small range of all of the colors of light, or as we say, electromagnetic radiation. And infrared is what we commonly think of as heat radiation. And so that's something that we need to keep the observatory very, very cold in order to detect heat radiation from objects very, very far away in space. And in fact, the science goals of Webb include detecting perhaps the farthest things we've ever discovered. One of the real advantages to infrared, as you see here, this is a Hubble Space Telescope visible light image of the famous Pillars of Creation. That's a giant gas cloud that's producing several stars inside it. Stars are being born. And when you go to the infrared, Hubble did have an instrument, NICMOS, that did see a little bit into the infrared. And you can see just what you're missing when you look just at visible light.
Console for a bit.
So those 2 images are both absolutely real. It's just that the second one is an infrared light, which is invisible radiation to your eyes. Infrared light has the ability to cut through dust. And this is one of the amazing properties. Just like you saw, if you want to see stars and planets forming, they do so inside giant clouds of dust and gas. And normally the visible light is completely obscured by all of that dust. There are other things like the very center of our galaxy. The Milky Way galaxy, which is a family of about a half a trillion stars that we belong to. The center of the galaxy is on the order of about 30,000 light years away from us, a light year being about 6 trillion miles, the distance light travels in a year. And that is also obscured by big clouds of dust. We can't see into the center of our galaxy, invisible light. So there are so many objects that infrared is going to be really, really excellent to see. We may also have some roll-ins. Oh, here we go. Yes. Here's a really lovely roll-in showing you that Webb and Hubble Space Telescope was designed mainly to see visible light, the kind of light that our eye sees. It did see a little bit into the ultraviolet and infrared. Webb is optimized and designed to see infrared. And amazingly, that allows you to see farther away in the universe. And that means farther back in time. The farther away you look in space, the longer light has taken to travel to you. And there's an amazing property of our universe. So the universe is expanding. Space itself is expanding. And as that light from the very early universe travels through space, the wavelength is actually stretched by the expansion of space. So light that might have begun from starlight and the ultraviolet or visible light from the first generation of stars, that wavelength of light has actually been stretched out into the infrared. And so if you want to see galaxies that are very far away and very distant, and here we actually see a graphic of how that works. A galaxy it seems to be receding from us in the expansion of space, and that light that would have started as visible or ultraviolet becomes infrared. So one of the amazing science goals of Webb is to be able to look back to a time probably only about 200 million years after the Big Bang. And this is the era that we think the very first stars and galaxies were forming. And so the amazing thing is the infrared light will allow us to actually see that far back, looking at the origins of galaxies and stars themselves. All right.
And Michelle,
so,
you can. Oh, I'm sorry. I'm just saying you can start to see, if you see, you can start to see that layer starting to rise up, layer 4 on that aft side. So slowly moving up now.
This must be very exciting for you. Can you give us a sense about your emotions right now?
But we like the grass to grow really, really slow. Yes, this is exciting. I mean, yesterday we did not think we were going to get through the first 3 layers, but the team, again, the entire team just executed everything flawlessly. We were only planning to do 1 yesterday, but that went so well. They said, "Hey, can we just keep going?" And we almost had to hold them back a little bit. It was the day was getting long, and we want to make sure they're well rested. But they were eager to go, and so they're all excited this morning getting these last 2 out.
This was one of the things that we were talking about the live broadcast. We've just been following exactly when this is happening. Of course, the communications team does not dictate how the observatory is unfolded. The engineers do it when the conditions are right. And people around the world have been joining us. I actually was talking to somebody who is a fisherman up in Alaska, and I was telling him that, okay, now things are going faster than we expected now. And the thing that he said to me was, you have to respect the catch. Whether things go slow and when the fish are biting, you keep going. And that's the amazing thing, that things were going so well that they decided to just go ahead and keep unfolding the Sunshield. So that's what we're looking at right now.
And Michelle, I think you're seeing 2 different rooms on the broadcast. We have 2 main rooms. We actually have multiple rooms, but our one room that's shown below there, that's actually our flight control room. So that's sort of the nerve center of the entire mission ops center, and that's where actually commands get sent to Webb. So you can imagine that's a key room. We have our controller sitting on the front row. We have our mission ops manager, who's sort of the ringleader controlling the whole show. He's in there right now, along with our management team. All of our ground communications to our ground stations around the world. Not quite sure what station we're on now, but Madrid in Spain, Canberra in Australia, and Goldstone in California. Those are our ground stations, and all those coordination with them is actually done from that room. Our timeline people, those are folks that are very, very busy creating schedules for us, minute by minute of operation. We change those timelines slightly every day, and they're just they're incredible at what they do, keeping us straight and keeping everybody on schedule. The top view there is actually our engineering support room. That's where our deployments team is, back in that back corner. We have all of our subsystems, our attitude control, our propulsion engineers, our communication engineers, thermal engineers, and our system engineers are all in that room, watching and watching over and making sure everything's safely progressing right now.
Excellent. But just for any people that are joining us now on our broadcast, you're joining us for the live commissioning of the James Webb Space Telescope. What's happening today is the very final stages of unfolding the large, incredibly innovative Sunshield that will keep this telescope very, very cold, and the ability to see very far into the infrared. Infrared light, as we were saying before, is a form of heat. That's how we normally think of it, as the way we experience it. But one of the things people often don't know is that objects that we think are very cold to human standards still emit quite a lot of infrared light. And as Keith had said before, the operating temperature of the telescope itself, once it's shielded from the sun, will be, well, Keith, it's pretty close to minus 400 degrees below zero Fahrenheit. Is that correct?
That's correct. Yeah, I like we in on our side we always use kelvins, which is an absolute scale from zero. So yeah, right around minus 400. Our telescope, our instruments. We have 4 instruments on board, and it's really those camera detectors that are not too much unlike your camera that you have on your phone, but obviously much more elaborate and cold. So it's those detectors that we're really trying to keep at that minus 400 degree rough temperature range to make sure they're absolutely the only photons of energy that are hitting those detectors are really coming from the object that Webb is observing.
And of course, it's an incredible idea to test something to that temperature. And I believe we might actually have some B-roll and some footage of testing of the Webb telescope. I remember that some of that happened at the Goddard Space Flight Center. We have a space environment chamber, which actually simulates going down to very cold temperatures. But then there was also testing done in Houston as well. Keith, maybe you can talk to us a bit about some of the tests that Webb went through before its launch.
Yeah, being a cryogenic observatory presents incredible challenges on the ground for testing. Testing it at room temperature doesn't tell us a whole lot. Everything about Webb is designed to be operated at these incredibly cold temperatures. So like the mirror itself, it actually is not a very good mirror at these temperatures. It actually gets better as it gets colder. So in order for us to test the optical system or the instruments, we have to take them into incredibly cold temperatures. So we did some testing at the Goddard Space Flight Center in Maryland. That's where we took our entire instrument package, put it in one of these chambers. We actually pump liquid helium around the walls of this vacuum chamber, and that's what drives us down to these really, really cold temperatures. Once that instrument package was tested at those temperatures, we introduced it to the telescope. And the telescope and the instruments were integrated, and it was too big for our facilities at the Goddard Space Flight Center. So we took it all the way down to Houston in Texas to the Johnson Space Center in Chamber A. Chamber A is famous for being built to test for the Apollo program. So again, we completely retrofitted, worked with our team down at the Johnson Space Center. Again, incredible NASA team between centers. And what we did there is we completely turned that chamber into an optical test facility that could be operated at our temperatures. And that again, an incredible achievement by the team that did that work. We were under vacuum and under test down there. I want to say well over 100 days. It was almost nearly 4 months. You can see some of the footage of us coming out of the chamber into the clean room. So this was after the testing was done. We had a team. We had pretty much the entire telescope and instrument team and spacecraft team down at Johnson Space Center for nearly 100 days. I think that was in 2017. So that was when Hurricane Harvey happened to come through Houston and presented some challenges for us and our team down there supporting that test. But we were able to test through that hurricane, that really devastated that area. And it actually, a lot of the people that worked on the facilities and were working at a Johnson Space Flight Center were highly impacted in their personal life by Harvey, but they kept at it and supported us. So that was quite a achievement for our team to. And nothing's been done like that before. We've never taken something this large down, an optical system, to these temperatures and been able to do that. So quite an really, really tough testing Webb on the ground. That's why we like it in space. It's at home. It's always wanted to be there. So that's why we're so excited where it is now.
Absolutely. Well, let's talk about, you mentioned it's home in space. It's going to a very specific location in space. It's not just going anywhere out there. It's going to a point that we call the second Lagrange point, or L2. And maybe you can give us a little bit of a talk about, where is this and why would we put Webb at the Lagrange point? What is a Lagrange point to begin with? How about that?
Yeah. So, these Lagrange points are interesting places where two large bodies like the Earth and Sun, the gravity of them sort of interacts in a way where you can put objects there and with some control, you can kind of keep them there. So what's really nice about Lagrange point 2, every large two-body system has 5 Lagrange points. We use Lagrange point 2, which is on the opposite side of the sun. So the sun line and the Earth, we're 1 million miles away from the sun on the other side. And what's nice about that, as the Earth goes around the sun, Webb just kind of tracks along with the Earth as it goes. In this animation, you can see, and we're always able to keep the Earth and the sun in a line with us, and that's really what lets us use a sunshade. Or Sunshield, like we have with Webb, that blocks out the Earth and the sun and keeps Webb in darkness all the time. The other nice thing about the Lagrange point is it is 1 million miles away, but that's really not that far. So it allows us to have a reasonably sized communication system. We're going to create gigabytes of data every day from our cameras and our instrument detectors. We have to get all that data to the ground, and we don't really need huge antennas to do that. So that's one nice thing about 1 million miles. Sounds far, but remember, we're sending data from Pluto and other missions back to Earth, and it takes a long time. So this is good for us. The other thing about Lagrange point 2 is it's far enough away from the Earth also that it creates a nice cold area for us to do that. So it's almost like it's just the best place to go if you want to do astronomy, especially, and if you want a cold telescope. And that's just everything about the architecture, the orbit, everything has been about getting this telescope cold, but in a reasonable distance to the Earth for communication.
Thank you for that. Again, for people joining us, you're looking at live coverage of the commissioning of the James Webb Space Telescope, the final stages of the unfolding of its huge, incredibly spectacular heat shield. And you're looking at a live image there from the MOC, the Mission Operations Center. That's at the Space Telescope Science Institute at Johns Hopkins University. So as you can see, there's all kinds of people standing around there. I know that for me, the last couple of days, it's almost been like a kid getting up on Christmas morning. I've been checking my email to see what was happening and how quickly this was going. And today we're looking at the final stages of unfolding this heat shield. This is truly one of the most incredible engineering marvels of the Webb telescope. There are many, but this is the first one that has to be accomplished before the rest of them can start to turn on. And Keith, maybe this is a good time for a look ahead. So, once we have, and I'm touching wood because we're still doing it, but once we have the Sunshield completely unfolded, what are some of the next things that need to happen before we have a full commissioned observatory?
Yeah, so for our Sunshield team, this is a big day. This is a big day for all of us to get this Sunshield out. So we will let them revel quite a bit for the rest of the team, for the rest of the deployments team that's still here, and for the rest of the commissioning. We have a lot of work to do. We got a long way to go here. So we'll take this as we get it. We take each one of our deployments as a small, it's a small touchdown, but the game's still going. So next up is our telescope, and that is, that's what it's all about. So starting this evening, we're going to get some heaters on to start heating up the motors that actually do the deployment of our secondary mirror system. We'll get that heated up. and we'll get on with that tomorrow. We'll start doing that operation. So that's really. Well, again, I got to make sure my timeline, depending on how long the day goes, we'll update everybody when we're actually going to do that. So our secondary mirror system comes out. You can see in this animation here. We actually have a lot of other deployables on Webb that we don't really talk about, not just because they're not as newsworthy maybe as the telescope or the Sunshield, but we have a lot of radiator shades we have to get out tonight on the spacecraft. The Sunshield and the telescope get all the attention sometime, but our spacecraft is critical that we control all of its temperatures, and we don't quite have all of the sort of the shields out to protect our radiators, which cool off our spacecraft. We have to get those out this evening. They're much more, I don't want to call them simple, but they're much more typical type deployments that we'll do this evening for the spacecraft. And then again, we get into our telescope deployments over the next couple of days, culminating in the 2 wings, which each wing has 3 of the 18 segments on it. So you can see we'll do that, what we call our port wing, our plus J2 side in our coordinate system. We call that port as you're looking forward, and then our starboard wing on the other side. So that should be later in the week, and we will breathe a big sigh of relief at that point, because we will have a fully deployed observatory. The next thing that our team will get into, I'm just listening to see when this motor move will start. This is our longest move, by the way, this one on the aft. So this is a very long move on the aft on layer 4 here. So that's why this is going on a little long. A lot of cable has to be drawn in for this specific configuration. But next, then we kind of turn over the telescope to the telescope team, hopefully next week. And what they're going to start doing is we have all those 18 segments. They're all locked down for launch. We actually sort of snub them up tight for launch. They're going to move those mirrors.
This is Dep Lead on ops. I can confirm the aft NPS which indicates that layer 4 is now fully controlled.
Here in the flight control room. Thank you.
Yeah, so that's layer 4. We're going to move on to layer 5 here. So you can tell the team, maybe we're getting old hat at this after 4 layers. I'm not quite sure. So yeah, when layer 1 yesterday was quite the celebration, and layer 2 maybe a little, still some celebration, but layer 4 we have to give it a little bit of love too, and cheer it on. So layer 5 is the big one coming up. But yeah, we're going to turn that telescope over to our telescope team, and they're going to move all those 18 mirrors off their launch stops. Each one will be moved a little bit. They'll go around all 18, and that's pretty much a 24-hour operation, and it's going to take them about 10 days to do that. So for a lot of us, we're looking forward to the grass growing even slower when it comes to deployment. So we're actually looking forward to a little bit of a pace break there, and actually let them. Our telescope team is sort of biting at the bit to get started, so they can't wait to get that going. So once they do all that, once they wiggle those mirrors around and make sure they move and track their positions, we'll be turning on a whole lot of other equipment. We're actually got our instruments. We're turning them on over the next couple of weeks, getting them going. We have a cryo cooler on board. I mentioned really, really cold temperatures. But we have one instrument that needs it to be really, really cold, and that's our mid-infrared instrument provided by our European partners. We actually have a cooler on board that takes that instrument all the way down to 6 Kelvin. So that's I don't know. That's getting really, really close to the minus 460 degree. Really, really close to zero there. So you see this animation of our instrument package in there. That's our 4 instruments buried in the heart of Webb there. So one of them is the mid-infrared instrument. It's kind of covered up there on the left side. And we actually are going to turn on a cooler tonight to begin circulating warm gas up through its plumbing supplies to make sure we don't get any ice contamination on the lines, because everything on the cold side right now is getting really, really cold, and we don't want any water ice to contaminate their cooler lines. So we'll be doing that tonight, actually. But yeah, all this is about that 29 to 30 days of on the edge. But over the next 2 weeks, it'll be a little bit slower pace, ultimately culminating in our final mid-course correction sometime in late January, which will insert us officially into that L2 orbit. And at that point, we would consider our spacecraft basically commissioned. And at that point, it's all about the telescope and the instruments, and we just can't wait to turn it over to them.
Well, you mentioned the MIRI instrument, and let's talk a bit about the sort of the whole instrument package that Webb has, the different instruments that are on it and the different capabilities they have. So do you want to sort of walk us through the four main science instruments?
Yeah, so we have a near-infrared instrument. Again, we're going to talk a little bit about the wavelengths that these are in. Our one instrument that's what we call the U.S. contribution to the instrument package is the near camera. That's been provided by the University of Arizona in a partnership with Lockheed. So they have built that. That is a fantastic imaging camera. That will be one of our workhorse cameras, doing a lot of imaging for us. The one interesting thing about that camera is they are telescope scientists.
I just want to let you know that those motor alarms that were.
Okay. Yep. So as you heard Nancy say there, we typically get some alarms, but over the course we've learned that those alarms can be dismissed. They're just routine now. So everything about, I mentioned all that data that comes down from Webb and any spacecraft. We have alarms on them to alert engineers if there's any problems, but we have a formal dismissing process, which she was just referring to. But so back to that near camera real fast. It is our workhorse. It also is our wavefront sensing camera. And what that means is that camera is used by our telescope scientists to determine the optical imaging quality that's coming out of our telescope. So they'll actually retrieve an image using near cam. They'll study it on the ground. They'll use that image on the ground to determine all the different settings that they need to do to align these 18 mirror segments. So that's our near camera. If you move on, we have a camera or another instrument called the Fine Guider and Nearest. That's another near infrared instrument, but it's also our Fine Guider, and that's provided by the Canadian Space Agency in partnership with them. And what that instrument does, it also does incredible science with some spectroscopy, and it also is our guider. So that guider actually works with our spacecraft attitude control system. It also works with our what we call our fine steering mirror, which is on the telescope. And all those systems working together actually help Webb point at whatever it's trying to image and take data from. We have incredible precision pointing, and we have observations that can be done up to 14 days. So we can hold steady on anything that we're looking at for 14 days. And the Fine Guider from Canada is a key part of that. We have a near-infrared spectrograph. Again, that's sort of a partnership between our European partners and the United States. And that is really one of our key science instruments. You're not going to get, the images out of that. What that instrument does is it breaks light down into its wavelengths, and that's really a key. I'll let you talk about that in a second, Michelle. I'm just say it, but that's a near spectrograph. I'm gonna let you go into breaking down light because that is key for what we're trying to do science-wise. And then we have this mid-infrared instrument, which is going further into the deep infrared, and that's really one of the key instruments for helping us confirm some other observations as far as how far away different objects are. But Michelle, you can definitely pick it up from there. I'm running out of my knowledge base on these instruments.
Yeah, this is the thing that, as astronomers, we're just so excited about. There's so many different components of Webb. I mean, not just the beautiful images that will be produced, but as you said, Keith, the idea of breaking light into its components is a technique called spectroscopy. And this is really an incredibly powerful technique because you might ask yourself, when astronomers say, we know what the stars are made of, they're made of, mostly hydrogen and helium, but usually a little smattering of everything else. When we see a star exploding and we say, we've just seen the generation of the element gold. How do we know that? And then there are also questions about, how do we know, for example, how far away a galaxy is, or how fast the expansion of the universe is taking something away? And all of that goes down to this technique called spectroscopy. So very simply put, spectroscopy is separating light out into a rainbow. That's really all it is. But the amazing thing is that scientists can then analyze very, very carefully how much light is coming in each color. And the graphic that you're looking at shows you. So this is light from in this case, from a star that has a planet around it. The idea is that there is an exoplanet, planet around another star. And one of the incredible science goals of Webb is to be able to analyze the atmospheres of planets around other stars. And if you can pass the light that's shining through the atmosphere of a planet, so the starlight is shining through the atmosphere of a planet around it as the planet goes through basically a little eclipse. It's actually in front of the star. And then you take that light and you separate it out into a rainbow. And we see here the graphic. So this is a planet. You can see that little dark disk represents a planet that's going in front of a star. And the planet has an atmosphere. There are different layers of the atmosphere here in different colors, green, purple, and a yellow color. And as the light from the star behind the planet shines through that atmosphere, then we get some amazing observations about what the atmosphere is made of. And if I could go to the graphic that we were looking at just a minute ago, when you actually take that rainbow of light and you measure the very jagged kind of squiggly blue line you see there is simply a graph of how much light is coming in each color. And the incredible thing is that different atoms and molecules, so for example, oxygen, or the molecule O2, which is how oxygen usually appears in an atmosphere, or say nitrogen or carbon dioxide, important molecules, water vapor, we can actually detect those molecules because every atom and every molecule will absorb light slightly differently. And if we can measure very carefully how much light is coming in each color, we can actually see the presence of molecules that are absorbing different color bands of light. And so here you see an atmosphere where it's possible that we can actually detect if there's oxygen in the atmosphere, or ozone, which is O3, 3 oxygen atoms, water vapor, carbon dioxide. And one thing that Webb may or may not be able to do, this is certainly very ambitious, is it might be able to detect things called biomarkers. And those are basically fingerprints in the spectrum that could be related to the presence of life. The main science goal, of course, is to find environments that might be Earth-like. They might be friendly to life. But you see something there called the vegetation jump. And that actually may be present due to plant life absorbing certain life. And while we don't know that this will be possible, the main thing that we're looking for are environments friendly to life. There is a small possibility that we could actually look at an exoplanet and see something that indicated a possible likelihood of life there. So that's something that's very exciting for us. So that's about spectroscopy. So these are all incredibly powerful techniques that we're looking forward to doing in the infrared. Infrared turns out to be the best place to do these. A lot of the most important molecules for life have very important absorption bands. They absorb light in the infrared. And so that's another incredible use of infrared astronomy. So just for those of you that are joining us, you are now looking, here we see an animation of some of the very important molecules for life. And as we mentioned before, as a planet goes around a star, some of that starlight shines through the atmosphere of the planet itself. And when that happens, we can look very carefully at the different colors that are absorbed. And we actually find out what chemistry is in that atmosphere itself. So you see that the starlight shining through the atmosphere of a planet around another star and eventually ending up inside the James Webb Space Telescope. And we'll be able to analyze it from there. So for those of you that are joining us, you are looking at live coverage of the commissioning of the James Webb Space Telescope. Today is an exciting day because we're looking at the completion of the commissioning, the unfolding, and in just a little while, the tensioning of the very last bit of the James Webb Space Telescope heat shield. I think that actually it might be a nice time to go to our social media feed because we will be able to take some of your questions live. For those of you that would like to do this, you could use the hashtag AskNASA. And I have been receiving some of the social media questions right now. So Keith, as we look in here at the live footage of the Mission Operations Center at the Johns Hopkins University, the Space Telescope Science Institute, maybe you and I can take a bit of a hack at some of these social media questions. The first one comes from one of our users on Twitter that says, will the telescope need periodic tensioning during its lifetime, or is this a one-off thing? So Keith, could you answer that question? Is this something that we're going to do again, or is this just the one time we ever tension this heat shield?
No, we do not plan to ever retension, and that was a chosen thing to do in the design. So all the materials, everything about the analysis of the design has shown that we don't need to do that. So everything will wear, but we have our layers are actually tensioned on springs. Over its lifetime, those springs will sort of take out any of those changes.
Let's see. We have a question. Somebody from Bob on Twitter is saying, how do you keep the Sunshield in the correct orientation? Does it require constant adjustments over time, or is the orbit set and it stays in the correct position forever? So that's a question about unfolding the telescope. Yes. Yeah,
it's locked in position. If this is its final position, it'll stay in that. Again, everything is designed to be a little flexible as temperature changes. Decreases in temperatures change. It will vary, but it's all
stations. This is Mom on Ops. All stations. This is Mom on Ops. Let me just give you a quick status of where we're at. You can see we've completed car 622, layer 4, and that call was made earlier. Before we get into layer 5 on car 626, we're going to go ahead and reassess our communications with our medium gain antenna and our signal strength there. So once we evaluate that and see if we need to repoint the dish or continue on, we'll take either of those actions before we proceed. So that's where we'll stay for just a little bit while we let the team in the back go ahead and do that analysis. So stand by.
Okay. I think you heard our mission ops manager there. We are playing the ops loop, right? How can I ask that? So we finished layer 4. This is live. You're getting to hear some of the stuff that goes on every minute of every day. And one thing we're trying to do is make sure our communication coverage is good. So they're going to take a little pause, it sounds like, to do that. So we can take some more questions while they get their communications established. Webb is communicating right now just fine, but sounds like they want to make some adjustments.
So we were just talking a little bit about the question that we got when we were getting that announcement from the mock. The viewer was actually asking about whether there's any sort of correction to the orientation needed. So, I mean, will Webb have any sort of engines to kind of keep its orientation right with its heat shield pointed toward the sun?
Yeah. So we move the entire observatory when we point. So all of Webb moves together as one sort of rigid body when we move around to look at things. So and we maneuver it with reaction wheels. We actually spin. There's 6 wheels inside. We spin those wheels up to different speeds. The torque on those motors, the Webb will actually spin around that. So it's the classic the bicycle wheel and trying to turn things up. You turn the other way. Webb has nothing to hold on to, so when those wheels spin, it gets spun the other way. So really, really slowly. So we use those wheels is actually how we maneuver and point. Every once in a while, we do have a propulsion system on all engines, and they can be fired too for more dramatic attitude changes.
Okay, well, looking, see another answer from Twitter. It says, is it extremely hot just behind the shield and extremely cold just in front of the shield? And this is a question that we talked about a little bit earlier in the broadcast, but there are people that are just joining us. Can you talk a bit about the temperature differential between the hot side and the cold side of the heat shield?
Yeah, so the hot side, that sun-facing layer, we've done everything we can to make it as cool as possible, but it's still really, really hot. It runs around the temperature of boiling water. You can see some of the temperatures right there. We roughly say 200 degrees Fahrenheit on that hot side. So each layer gives us about a temperature drop. So the cold side layer, it runs about we're in Celsius or whatever, but in kelvins, the warm side is roughly about minus 350 degrees Fahrenheit. And then that telescope is right around minus 400. So that kind of gives you an idea of that differential. Check out our Where is Webb website, and that'll kind of give you a flavor for the temperature differential.
You were mentioning the Where is Webb website, and that can show you actually, where the observatory is on its way out to L2. And one of the things that we actually mentioned briefly at the beginning of the broadcast, but we haven't had a chance to go into any detail, is the fact that there was something happened during the launch that was actually very, very fortunate and will extend the life of the observatory, we hope. So Keith, give us a sense about what that was. What happened and what was the advantage of it?
Yeah, so again, going all the way back to launch day, we asked Ariane to give us a velocity when they separated from us in that video. So we specified exactly what velocity, which is speed and direction, we wanted from them, and that velocity that we spec'd from them is what was aiming us towards L2 at the right speed that we needed. However, there is some small errors to that, and we don't quite know how big those errors are. So we plan for the worst case. And Webb will need to use its onboard propulsion system to sort of make up that. But since we got such a good trajectory or good performance out of the Ariane 5, which we kind of we would, given their history of good performance, we didn't use as much fuel as we needed for that first correction. We had designed everything in the system. If everything goes worst case, we would still have at least 10 years of mission life, but basically everything went best case. So we have significantly more than 10 years. We don't have the exact number yet, but eventually over commissioning, as we continue to study our propulsion system, as we continue to learn more about how Webb operates, we'll fine tune that number and get it out later in commissioning. But then when the number comes out, I think everybody will be really, really pleased that we're significantly use less fuel, and we're going to significantly exceed that 10-year mission life of fuel. Yeah.
Excellent. All right, going back to our social media questions here. Let's see. So we have somebody named Sunfrog on Twitch is saying, how much space is between the shield layers in inches or feet? How far apart are these different layers we're looking at?
Yeah. I don't know if they can roll that test roll again from the test that we did. It's roughly 1.5 feet. Roughly 1.5 feet. The whole, it's about 6 feet from one side to the other. So depending on where it is, it's a little bit thinner on one, down towards the short side, and it's a little bit further spread on the fore and aft, as you see in that OVT right now. So yeah, roughly 5 to 6 feet of separation, 1 foot between each layer. I don't know what that is. Maybe it's not that far apart, but that's all it takes to provide the cooling.
Excellent. All right. Let's see. John Haig on Twitter asks, what would happen if the Sunshield tore while you were deploying it? Is there a backup for this? There were actually several different questions that we got about this, about little tears or anything.
Yeah. Tears are a big concern. And then again, everything that's been done as far as the design, if we do get a tear, what concerns us even more than a tear is that tear propagating throughout the entire Sunshield. So what we have a system of rip stops incorporated into each layer. So if we do get any small tears, it'll only go a short distance and then stop as we have reinforcements around. So that's all been incorporated into design. And then again, everything you're seeing about the deployment, why it looks like it's grass growing, is to be slow, methodical, so we make sure that we're not putting any stress on the membranes.
Excellent. So one of the things that people saw when they actually went to the website, Where is Webb, is that the web appears to be slowing down right now. So can you give us a sense about why? Why would it seem like Webb is slowing down?
Yeah. So really, it's we as we leave the Earth, we're going to L2. We're going to that 1,000,000 mile mark, and then we kind of, in very simplistic term, think about we stop. We don't really stop, but we with our relative velocity to the Earth. Remember, as we go around the sun, Webb is going with us, and it's always maintaining that 1,000,000-mile distance. So essentially, we're stopped with respect to the Earth. So we left. We were several kilometers per second in our speed when we came off the Arion, and as we get further and further from Earth, the Earth's gravity is slowing us down, and we're trying. Everything is about making our speed just right. So as we get about 1,000,000 miles away, we get into that L2 orbit. So you'll see that slow down more and more as we get closer to our L2 orbit insertion.
Thank you. So I just got the message that we're going to take a brief pause in our commentary while they look at some communication up to the telescope. We will be back, and we will be taking more of your social media questions. You can use the hashtag #AskNASA. And I'm Michelle Thaller here with Keith Parrish, and you are looking at live commissioning of the James Webb Space Telescope, the final phases of the unfolding of the heat shield. And we will be here throughout the process. We'll take a brief pause now, but we'll be back very soon. So thank you so much for joining us.
Yeah, Mom. We can talk about that later if you want, or I can talk to you now. Yeah, we will execute 12.
OC, this is Mom on Ops.
OC on ops.
Yes, sir. We're going to go ahead and get ready for car 626. Are you ready?
OC is go.
All right, copy that. MSC, are you go?
Yeah, MSC is a go.
Copy go. SI, are you go?
SI is a go.
Copy go. Wavefront, are you go?
Wayfront is go.
Copy goes. All stations, this is Mom on Ops. We're a go at this time to finish Sunshield tensioning, layer 5. OC, this is Mom on Ops.
OC.
Yes, sir. You can go ahead and pick up at step 2 of car 626, and you can coordinate with DepOps on this loop.
Copy that, Mom.
And OC, you will be executing steps 1 through 12, 12 inclusive, 1 through 12 only, and then we will hold.
Copy steps 1 through 12, including 12.
Thank you.
NOC, this is DepOps on Ops.
Go ahead, DepOps.
Yeah, so when you're ready, we can go pull up 626.002, DEU to frame 8.
Copy that.
That proc looks good. That command line looks good. You're good to execute.
Executing.
And you're good to continue.
Copy. Go to continue.
Okay, I can confirm operations frame 8. And at step 626.0, we are below the temperature, 290, so we do require self-heating. And we have Oscar 349 for step 626.004.
Copy that, DepOps. We have CR 349 queued up in the central window now.
Yeah, I see that. I don't see it on the command line, though. The CR looks good. And that command line looks good. You're good to execute.
Executing.
And you're good to continue.
Copy. Go.
Okay, stand by while we review the motor move parameter.
Standing by.
And OC, the parameters look good. You're good to move the plus J2 mid-boom motor.
Copy. Go.
And in the yellow window, you can queue up the stop.
Roger.
And we will hang out here waiting for the motor to warm up. OC, this is DevOps on Ops.
OC, go ahead.
Okay, at this time, you are going to execute the DU stop deploy at step 5. The
Copy
command
that.
line looks good. You're going to execute.
Executing.
And you're going to continue.
Copy, go.
Okay, I can confirm motor stop. And then we are going to execute the motor move at 626.006. And that command line looks good. You're going to execute.
Executing.
And you're going to continue.
Copy, go.
Stand by while we review our motor move parameters.
Standing by.
And OC, you're going to move the plus J2 mid-boom motor.
Copy, go.
And the motor move, status is moving.
Project Science to Mom Ops and stepping off console. Step lead on ops. Deployment status update. I can confirm the plus J2 latch on layer 5.
Thank you, DevOps. That's good news. Good news.
OC, this is DevOps on Ops. You are go to execute DEU stop deploy.
Copy, executing.
And you're go to continue.
Copy, go.
No.
And I can
You're watching
confirm
live
your
coverage
stop.
of the historic event of commissioning the James Webb Space Telescope. Today we are looking to actually
We at
finalize the tensioning of the
626.008
amazing heat shield.
Our NBA
The
temperature
fifth
is
layer
below
of the heat
290,
shield has
so we're
begun
going to
tensioning,
continue with
and
Oscar
we are going to be continue with you
350
through this amazing event.
to do our
Our
motor
live
self
coverage
heating.
and commentary will be resuming at
Copy that,
11:30
DevOps.
a.m.
Stand by
Eastern
while we
Time.
queue up CR
So
350.
please submit your social
Maybe
media
bye.
questions using the hashtag AskNASA, and at 11:30 a.m. Eastern Time we will begin our live commentary again.
I can see that, Oscar, and that looks good.
The fifth layer of the heat shield
And
is
the
currently
command
being
line looks good.
deployed.
You're good
It's
to
currently being
execute.
tensioned, so
Executing.
everything is going well. We'll see you in just a few minutes.
And you're good to continue.
Copy, go to continue.
Stand by while we review our motor move parameters.
Standing by.
And OC, you're go to move the minus J2 mid-boom motor.
Copy, go for move.
And then OC, you can queue up the stop command in the yellow window.
Roger.
And the minus J2 mid-boom motor move, status was moving and it's gone to hold. We are going to stay here until we reach approximately 293-ish. Okay, and OC, we can execute the DE stop deploy at this time.
Copy. Executed.
And you're going to continue.
Copy, go.
And I can confirm the motor stopped, and we're going to continue with 66.011. And that command line looks good. You're going to execute.
Executed.
And you're going to continue.
Copy. Go to continue.
Stand by for review.
Standing by.
And OC, you're going to move the minus J2 mid-boom motor.
Copy. Go for move.
And the motor status is moving. Oh, and OC, you can queue up the stop command in step 12.
Roger.
Project Science, this is Mom on Ops. Report to the flight control room, please.
Project Science, welcome.
Step lead on ops. I can confirm the minus J2 latch event for layer 5.
And OC, this is DevOps. On Ops, you are go to execute the DEU stop deploy.
Executing.
And you're going to continue.
Copy, go.
Okay, and I can confirm that the motor move is stopped. We're ready to continue with 626.013. DEU to operate frame 0. Command line looks good. You're going to execute.
Execute.
And you're going to continue.
Copy, go.
Okay, I can confirm operations frame 0. And at step 626.014, Dep Lead has confirmed the team is ready to continue. And we're ready for 66.015. The command line looks good. You're going to execute.
Hitting.
And you're going to continue.
Copy, go to continue.
And stand by while we review motor move parameters.
Standing by.
And OC, you are going to move the forward MTS motor pair.
Copy, go for move.
And the motor status is moving. And OC, you can queue up the stop command.
Roger.
I'm here.
Hello, you are watching the live commissioning of the James Webb Space Telescope. Today we have the exciting news to bring to you that we are looking to finish the unfolding and tensioning of the heat shield. And right now they are working on the final layer, the fifth layer of the heat shield. And I'm Michelle Thaler. I'm an astronomer at Goddard Space Flight Center. And I'm working from my home today because of the COVID pandemic. So I ask that you all give us some patience with this broadcast. We want to make sure that people have a chance to see live this wonderful and historic event. And I'm joined by Keith Parrish. Keith is actually right now live at the Space Telescope Science Institute at the Johns Hopkins University in Baltimore. And above us, you can see live footage of the MOC, or the Mission Operations Center. And this is where people are working on the heat shield right now. So, Keith, we took a brief pause in our commentary. Could you bring us up to date? What is going on right now with the James Webb Space Telescope?
Yeah, so we took a short pause. We're currently all of our data coming down from Webb is coming through our Canberra ground station on Australia. So shout out to our Canberra folks down there. We're currently in communication with them. We'll be in there for another couple hours until we hand over to our Madrid station in Spain. So we took a little pause. We always want to make sure we're good to go before we go into the next operation. So it took a little pause to make sure all of our communication with Canberra was solid, and it is. So we just resumed layer 5 tensioning, and we actually have done we have 6 corners to tension, and we've tensioned the first 2. We are actually currently tensioning what we call the 4, the 4 side, which you can see up on what we call our observatory visualization tool right there. And you can see just a little bit of separation up there at the top as that layer spreads on that corner.
And once again, for those people that are just joining us, the graphic that you're seeing to the left of your screen is actually correct in real time as to what Webb is doing right now, and that's based on data and telemetry coming down from the telescope. Is that correct, Keith?
Yeah, that's right. So all that information is coming down from Webb right now. Our team that created this, what we call the OVT, that's our acronym for it. It takes all that data and it creates this visualization of what's going on Webb, and it really kind of gives us a connection to Webb, and is what it's doing. We know this isn't a live shot of Webb, but it really does give us sort of that spatial awareness that the engineers need. Again, it's really about the data, the ones and the zeros, and all the telemetry that's coming down, and we have thousands and thousands of data points coming down. So we take all that data and we make these images to tell us exactly what physical configuration that Webb is in right now. And you can see you can kind of see as you go down to the I do have my model here. I don't know if I can throw it. So what we are doing right now is we're tensioning up on this side right here. You can kind of see a little bit this front corner here. We've already done the fifth
Keith,
layer.
Just a note to the directors of the broadcast. Could we get a picture of Keith?
Oh, I'm sorry. I'm pointing to something you can't see. Yeah.
Can we get Keith back on camera? Thank you. There you go.
There we go.
There you are.
I'm big too. Okay. Yeah. So this is a model of and I got to get it right here. So we're actually tensioning up right now. You can see on our OVT when I'm not on camera, you can see this is what we call our forward part of our Sunshield, and we're tensioning layer 5 right there. If you swing around this way, we've already done these 2. We've already done this side, and we've already done this side. So right now we're on 4, and then we'll eventually do our aft. This is our aft side. We'll do that, and right after we finish our 4. So yeah, we're running out of cables to wind up. We started out yesterday moving 90 cables. And right now we're down to our last 18 cables. So the team has been winding those up and that's what actually creates that tension on the Sunshield.
We've gotten some questions from social media, and remember that you can use the hashtag #AskNASA if you'd like to ask some questions live. And there's a couple actually that talk about the shape of the Sunshield. So there's why was this shape determined? This person says, why wasn't it oval shaped or circular? Can you give us a sense about the design of the Sunshield and why it looks the way it does?
Yeah, the Sunshield is actually shaped. Basically, it's no bigger than it has to be. Any larger than it is, and that would have been even more engineering challenges. So we have requirements on how much sky that the telescope can see at each time, and then the shape of the telescope, the shape of the Sunshield, lets us pretty much observe 60% of the sky at any time. So we can pitch forward with respect to the sun, and still keep our secondary mirror in shadow. We can pitch back quite a way, well over 50 degrees, and still keep our telescope in shadow. So we can kind of tilt the telescope back and forth quite a bit, front and back. Now on the sides, we only roll about 5 degrees each way to the side. So that's why the Sunshield has this sort of narrow shape on the sides. It's 50 some feet on the sides, and it's 70 some feet long on the length. And then instead of making it a square or a rectangle, we don't need it to do that. So we tried to limit as much material as we had to handle on orbit. That's what gives it this sort of iconic kite shape, is that it didn't need to be anything other than a kite to provide that provide our telescope with that view of the sky at all times.
And I should just say as a shout out, that was Andra on Twitter that asked that question. And then as we see, there's a graphic up here about just how much temper differential there is between the hot side and the cold side of the heat shield. One of our social media guests asked, does the observatory itself, does the mirror itself pan around a lot to look at the sky?
On ops. Another deployment status update. I can confirm the latch event on the forward MTS pair for layer 5.
Okay.
All right, good news, Dep Lead. Thank you. Good news.
Okay, so what you just heard there, you just heard our Dep Lead, Hillary. She just told us that we are finished with the forward. So we've done 4 of our 6 corners.
And OC, you are go to execute.
Spin that image around to the backside, and we got 1 to go. So we're really getting down to the finish line now. So back to your question. Or back to the question, we maneuver the whole observatory. The whole observatory maneuvers to look at whatever it's imaging, whether it be a galaxy or other object. There was early studies to actually move the telescope relative to the Sunshield, and that's a really complicated thing. So
operate frame 10. Command line looks good. You're go to execute.
Executing.
You'll hear us being interrupted by live updates from the MOC, the Mission Operations Center. So don't worry if we're pausing. We're listening to what they're saying.
Yeah, exactly right. So that's our Dep Ops engineer, Nancy. She's communicating again with our flight controllers in the room to communicate what commands that our deployments team want to send up to Webb. So again, we just maneuver the whole observatory. It's just better to maneuver it, make it nice and rigid and solid on orbit, and just maneuver that versus trying to maneuver the telescope individually.
And I can confirm
That's what really drove that Sunshield shape and size.
66.018, I have confirmed that Dep Lead and the team are ready to continue. So we can go to 626.019. And that command line looks good. You're good to execute.
Executing.
Are you starting to get excited, Keith?
Yeah, well, that was the command. We're actually sending the command to start turning those motors.
Happy go.
So let's talk a bit about the importance of the Sunshield, and there are many different aspects of that. This really is an exciting piece of technology, and this is something that for a space observatory like this we've never tried before. Can you give us sort of a pan back, sort of the 30,000 foot look at why this Sunshield is so incredible?
And OC, you're going to move the aft MTS motor pair.
Copy.
There we go. So. I do like to let people hear the commanding there because it's really, it's interesting.
Roger.
There's there's more than just one command that goes up. Our flight controllers and our DepOps lead they're checking everything that's coming back and making sure that the next command is the right command. So they're double checking and double checking. So that's a lot of the back and forth you hear there. But as you can see on the graphic there, you'll see our motor counts.
Motor pair status has changed to moving.
Yep, there we go. So you'll start seeing those counts. That's what we call a field director, which keeps track of our motor position, and you'll see those counts starting to increase as that layer is separated and those cables are wound in. So I think the big, back to your question, the big challenge with this type of deployment is we're doing 5 layers. We have to handle 5 layers, and everything. We're pretty good at deploying things that are rigid, but the membranes are rather they're floppy and they want to float around. We have cables that we don't want to get slack, so we're really trying to do an intricate operation right now, 560 some thousand miles away from the Earth, and control every aspect of the position of these layers. And I think that's really where the challenge has been, is to make sure that we understand every second of the deployment where these layers are. So there's a lot of features built in that aren't really apparent in any of the things that you're seeing right now that keep these layers very controlled and make sure that they're not floating places that we don't want them to be. And that's really been the really one of the challenges for such a large sort of floppy deployable item that this Sunshield is.
Speaking of it being kind of large and floppy, we've gotten several questions on social media. So Shivani from our YouTube feed asks, what happens if even one of the Sunshields get damaged? And there are other ones about micrometeorites. So, tiny little bits of rock flying around in space. Well, how resilient is this heat shield to something like that?
Oh, it's everything from the materials that sort of its raw materials that was chosen for its strength. To be able to handle the environment of space, what it's coated with to make these really colors is coated. Is everything has been designed. It's got lots of reinforcements. You can see in some of these this video of the real shield now. You can see a lot of seams. I do want to give a shout out to our membrane. We had a vendor that created these membranes and had to stitch them all together, so to speak. And it's completely reinforced so that if we do get tears, they won't propagate. And as far as micrometeoroids, we do expect to be hit with micrometeoroids. The good thing is that they're not very big and they won't do much damage. So we actually, one of our early developments for this material is we actually took it and hit it with high velocity projectiles moving several kilometers per second to make sure that the material could withstand that. So over the lifetime, we do expect really, really tiny microscopic holes to develop, but again, that's all accounted for in design. So it's rather rugged. Once it's all tensioned up, it'll be fine.
And you were talking about the fact that this is this sort of large, huge sail that we're unfolding little bit by little bit in space. And of course, while there isn't any air or atmosphere where Webb is, there is something called the solar wind. And the solar wind is actually a wind of high energy particles that are coming off from the sun. So not a wind in the way we think of it, but a wind of actually high energy particles. Does the solar wind have any effect on the heat shield and its pointing? Oh
yeah, so we get something called solar pressure. And again, if the whole concept of solar sails, to possibly travel around our solar system, with free propulsion from the sun. It's a very small force, very, very tiny. It's not like the wind blowing, but it is a force. It's a physical force. The sun, the solar pressure that hits the sun shield. So we have to account for that. It will try to move us around. The biggest thing that it does to us is it's offset. So what I mean by that is the solar pressure will tend to try to turn us, and we counter that turning force with some reaction wheels in the spacecraft. And then ultimately, those wheels get spinning so fast we have to fire our onboard propulsion system to unload them. And that takes fuel to do. So I think earlier in the week, we deployed something called our aft flap off the back of the Sunshield main structure. And that aft flap is intended to sort of a sailing analogy, sort of to counter, almost like a little bit of a rudder to help us counter some of those forces. And ultimately that leads us to using less fuel on orbit.
And is that's something that is a limitation to some degree for this observatory. It does have a finite amount of fuel to do that. Is that correct? That'll be one of the lifetime limitations?
That's right. So, fuel is our only known limiting life item on board. So obviously we wanted to take a lot of it. And we worst cased everything. And then we said, hey, once we worst case all of our conditions, meaning we don't get a very good injection from our Ariane 5 vehicle. We do all of our burns late. They're not very efficient. We have lots of momentum that we have to unload, lots of solar pressure. If all those things go bad, we still want 10 years of fuel. And so all of our worst case calculations is how we came up with how many kilograms of fuel to take on board. Fortunately, so far, those worst case conditions, I think as Amy said yesterday, we conservative. So all those conditions so far have not been on the worst case. Our execution of that first burn, and again, everything has been really, really good. So we expect to use significantly less, and we expect to have much more than the 10 years.
And I'll just mention that the question about the solar sail effect on the heat shield comes from Alan on Facebook. So thank you very much for your question. There's a question coming in that maybe I could take a bit of a crack at answering myself. And Keith, certainly you can chime in on this. But Mike on Facebook asks, who will be able to use Webb? Just NASA. And I think this is a chance to kind of talk a bit about the international nature of this mission. Mm-hmm. So absolutely, it will not be just NASA that is using the Webb Space Telescope. The Webb Space Telescope has several major international partners. Our big partners are the European Space Agency and the Canadian Space Agency. And so there is a time allocation to the major partners in this mission so the European astronomers, people working with the European Space Agency and also the Canadian Space Agency. However, like Hubble, the Webb telescope is a world observatory. And what will happen in the future is that there will be committees of astronomers that every year will review proposals from all over the world, from teams of scientists who want to use the Webb telescope for their own research. And again, while the main organizations responsible for the operation and the building and testing of Webb will have some time allocated to them automatically, a lot of this will be open to the public in the sense that professional astronomers from all around the world will be able to use it. And it's not just the observations themselves. The other thing that's really, really important to talk about is the archive. That the data taken by the Webb telescope, when you're an astronomer, say, I actually have been honored to use the Hubble Space Telescope myself in the past. You write a proposal to this committee of scientists every year that then ranks the proposals in terms of their priority, their science priority. And then you get your data, based on whether you make that priority list. And if you don't, you can apply again next time and all of that. But that all goes into an archive. And that archive, after a certain amount of time, is public, and anybody can use the data. So if you're a scientist that's won the proposal, you should get a first chance to look at your data and make your discoveries and observations that you want to. But then eventually that data gets put into an archive where anybody can use the data. So this is a world treasure. It's not just NASA that will be using this observatory, and it's not just NASA that built the observatory and launched the observatory. This has been an international program from the very beginning. So that's something we're very proud of. Let's see. So I know, I'm getting, more and more excited. The heat shield was a tremendously complex part of this observatory. So for people that are just joining us, maybe you could give us some sense, Mike, a little bit about the number of actuators, maybe talk about what an actuator is and the number of things that had to happen to get this thing to unfold into tension. It's something that, all of us are just, thrilled to see happening so beautifully in front of us. Can you give us a sense of that? Yeah. So, one of the big things that, as we've talked about is the amount of mechanisms that we use, specifically the pin. So when we fold up all these layers,
we have to sort of secure them to the primary structure, which we deployed back on day 3 after we launched. So those pins, there was 107 of them. And we had to sort of spear all the material, put holes in the material, and actually push them through to connect to our structure. Here you're seeing our solar array come out in this graphic. Again, we were able to capture that live on launch day, and that's that antenna that's currently communicating with Canberra. So here's these forward structures. All of the material that's now out, was pinned to this structure, meaning it was actually there was 107 pins that went through it and actually held it down to that structure. And we had to release all 107 of those pins, and we did that over the last few days. And then we had this cover roll up. This cover rolls up as we release those pins. You can see the aft going there, and on the front you can see our cover rolling up as we release these pins. Now this was our big event on New Year's Eve when we released the final set of pins and the covers unrolled, and we actually used these telescoping booms to pull out all 5 layers. So this was quite the big event for us as far as changing Webb's overall appearance. It made a dramatic change in our temperatures when we did these 2 booms. Again, you can see that cover rolling under right there. And this is our other side coming out. So I think releasing those 107 pins was quite an achievement. Again, because one doesn't release, then our membranes are trapped, and we would have had to go into a different contingency operation. So again, you're seeing what's going on right now. This is old footage of when we tested the Sunshield on the ground for the very last time. So everything you're seeing in this video right now, in this time lapse, which is probably just a few seconds long, is taking us yesterday and today to do. So you can see in this time lapse, the last layer's tensioning up, and you can see what a dramatic change that it takes as it is stretched out like that.
And we have a question from Gray Squirrel on Twitter, and this is one that maybe I can take to give you a little bit of a break, Mike, but but you can jump right in. So Gray Squirrel on Twitter asks, why does it take until June to start science operations with the James Webb Space Telescope, and what else needs to happen after reaching L2? And I think this is a chance to give us a little bit of a look ahead about what's going to be going on after today and after the heat shield happens. So one of the things I can say is that a lot of this has to do with cooling the telescope down. This is an infrared telescope. The reason we have these incredible heat shields is so that the observatory itself can be very cold, very sensitive to the infrared radiation from space. And so the things that will be happening in the next few days, personally, I'm really looking forward to the deployment of the secondary mirror. There are these very large boom structures that will come out in front of Webb, and that will bring the focusing mirror. The primary mirror is that beautiful 18-segmented gold mirror that all of us have been talking about. But then there's also the secondary mirror that needs to come out on these booms that all of these 18 mirror segments will focus the light up to. And then that light will be actually reflected back down into the instrument package for Webb. And so that's one of the big deployments that will happen in the coming week. Just listening.
Exactly right. That's our next one that we're really, really excited about, because that's, again, the Sunshield is great engineering. It's absolutely needed for this mission, and it's incredible. But the Sunshield is there to cool what we really want, and that's that telescope and those science instruments. So we really want to get those deployed next.
And then after that, we have the full deployment of the primary mirror. So that 18 segment mirror has 2 wings. The wings will both be deployed. So you can see here in this animation, there's the secondary mirror that's coming out on this large boom. That's the focusing mirror. And you can see that it will be focusing things down to the sort of that black protrusion coming out of the center of the gold mirror. And then after that, the 2 wing segments will also be deployed. And once that happens, we will have the fully commissioned and huge
thing is it takes about 2 months for our telescope engineers and scientists to sort of align it and sort of focus it, so to speak, and to make it working at an operational as an actual telescope. And then it takes another couple months alongside of that. It takes another couple months for our instrument teams to get their instruments calibrated and get them all checked out. So it all adds up to about 6 months before we would actually get some of our first science. And that cool down drives a lot of what we call our entry criteria. Like we cannot let the telescope can't do certain things until it reaches certain temperatures. So that cool down on top of these really, really precise operations that our instrument and our telescope teams need to do all kind of add up to that 6 month period or 4 months period on top of the, what we're doing right now in this first month, 1 2 months.
You've heard us say before just what a technological marvel the Webb telescope is. And talking about some of these deployment activities, these commission activities that are going on, Keith there mentioned the idea that the alignment of the mirrors needs to happen. And of course, we have 18 wonderful gold-coated segmented mirrors, but they all need to work as one continuous telescope mirror. And so part of this commissioning will be to actually do focusing of each of the 18 segments. Keith, maybe you give us a sense that the segments can all move independently. Is that correct?
That's right. They can tilt. They can move in a lot of different directions. And again, it's not a lot of movement, but they all can move in different directions to align themselves. They can also be pushed and pulled a little bit to sort of change their radius of curvature a tiny bit. So all those different movements have to be well coordinated, and it's quite the challenge that the optics team has coming up for them to do that. So that's really groundbreaking. Really groundbreaking what they're getting ready to go into, which is aligning those 18 segments. So they have full control over all of them. But even though they have full control over them, they have to get the data back down to the ground or where they are. And again, a lot of ground system processing to compute the next move, and then they'll just keep cycling through. And at the same time, they're imaging. They're taking reference stars to make and using those reference stars to help them align and focus the telescope. It's a very painstaking process. It's groundbreaking, but it's going to be really something when they get it all done.
And one of the other parts of the commissioning that I think is just incredible is that because this telescope is operating at just low temperatures, a lot of people are familiar with the idea that materials expand and contract and change shape as they change temperature. And so these mirror segments, which are made from beryllium, it's a type of metal that behaves very well under very cold circumstances. It keeps its shape, it works very well. The beryllium segments actually were ground to a curvature that isn't correct when it's at room temperature. They actually need to cool down to this operating temperature that we said, which is close to minus 400 degrees Fahrenheit. And it's only at that operating temperature that the curvature of the mirrors are correct. Is that right, Keith?
Yeah. And again, that you're going back, again, the development history is just doing that very operation and making those mirrors. So we'll stand by. I
see something happening in the mock. People are getting excited.
Okay. Here we go.
I can confirm the final latch signature on the aft MTS, which indicates that all 5 layers of the Sunshield are fully tensioned.
How exciting.
Significant milestone accomplished. Job well done, Sunshield team. Job well done.
Yeah, so.
Thank you, Mom.
All stations, this is Mom on Ops. All stations, this is Mom on Ops. Stand by for PM.
Hey guys, I just want to congratulate. This is Def Ops. You can go ahead and execute GE stop deploy.
Copy. Executing.
This is incredible to see. We're watching live footage of the mock, the Mission Operations Center. It looks like we are very close to declaring victory on the deployment of the Sunshield.
Yeah,
and I can confirm motor stop. We'll stand by here.
Congratulate our team downstairs.
Whatever they want to
do. Many years in the making, right here. So not just for NASA, all of our industry partners. It's just an amazing achievement. So I just want to congratulate our Sunshield team right now. What an achievement.
Okay. Hey, I just want to take a moment to congratulate everybody. This is a really big moment. We have a bunch of work to still do, but Sunshield has been unbelievable after many years. Sorry about that. Since I don't normally talk, we bring the mic down. Anyway, so I said this is a really big moment. I just want to congratulate the entire team. We still got a lot of work to do, but getting the Sunshield out and deployed is really, really big. You constantly reinforce what I tell everybody, that the JWST team is the best in NASA. There is, hands down, nobody better than what we have here. You guys should all take pride in all these accomplishments. One of the things I've told folks, and I've even put in emails, this is so unique what we do in this mission. We are going to be bonded forever by what we experienced, through not only just through operations and with the mission ops team, but over the last, all those who've worked on it over 20 plus years. And finally, I'll just tell you what I put on Facebook last night when I shared the story. I just said the JVS team kicks butt. I didn't use the word butt. I used another word, but I won't use that word here. Congratulations, everybody. Hoorah! Hoorah!
Absolutely awesome. So yeah, this is we'll let our celebrations continue. This is incredible. What an incredible week. But folks like me are looking ahead right now. I'm looking ahead deployment and can't wait to get that out. So but congratulations to our entire team. Just awesome. And just want to pass along some thanks to everybody viewing this, everybody who's been rooting us on.
And all stations, this is Mom on Ops. We're going to hold right here for just a moment. All stations, this is Mom on Ops. Just hold right here for a second. Enjoy your moment, and then we'll pick up with that.
Just as you said, it's so wonderful to have all the people that are joining us around the world for this event. This is truly incredible. When I first saw the design of the James Webb Space Telescope and just the ambition of it and the size of it and the scale of it and this giant heat shield that needed to come out and so many things needed to work, it took my breath away. And I'm here. I'm actually getting goosebumps. I mean, this is a wonderful, wonderful time. How are you feeling, Keith?
Oh, yeah, it's just, like I said, half my mind is going, woohoo, and then the half of my mind's going, let's get that, we got to get that secondary mirror out. So that's just how my mind thinks. So, but that's good. But no, this is really good. I mean, and Webb is absolutely, hopefully everybody is becoming iconic a little bit. It is absolutely a beautiful spacecraft. We did not design it to be beautiful. We designed it to be functional. But as a fact of making it functional, it's absolutely a stunning spacecraft. I did get to spend a few minutes with it in the clean room before we shipped it down to launch, and I was just amazed at just how beautiful of a machine it is. So, and that machine is really a function of hand built by this team. So, so a salute to them.
Absolutely wonderful. So to confirm, Keith, we have final confirmation that the heat shield is entirely extended and tensioned.
All stations, this is Mom on Ops. We're gonna jump back into the cast here and continue with the coolest thing in space. There is nothing cooler in space than JWST. That's a fact. So, OC, this is Mom on Ops.
OC on Ops.
I love that. The coolest thing in space. It will be soon.
As you can tell, even though we finished this up, we're going to move on to this evening's activities right off the bat. So we have some more 24-hour operation there, and we're constantly
at 626.021, Dep Lead has confirmed that the membrane tensioning is complete. So at this time, we're ready to continue at 626.022, DEU to standby.
Copy that.
So what's going on? What's going on now is our we're going to start shutting down or reconfiguring our electronics and turning off our motors, and basically tell our electronics that have been driving these deployments that their job is done. Thank you very much. You did your job, and now you get to move on to your next thing. So that's what they're doing right now. They're just basically shutting things down and getting configured for the next operation. So you may hear some of that.
Well, just many congratulations, Keith. This is just incredible.
Yep.
So awesome. You hear about the preparations. Sorry.
No.
I didn't mean to step on you there. You've heard about the preparations.
I'm sorry. I keep stepping on. I just want to thank you guys for putting these productions together, because it's just awesome to bring
standby mode round
out there.
We're ready to continue with 626.023. And that clock looks good. You're go to continue or go to execute.
Executing.
Okay.
So as Keith just said, they're getting ready to do the next things that will happen, and please note that we will be bringing you live coverage of these other major deployments. So the next one I believe will be the secondary mirror, and
you're good to
I don't know
enable.
exactly the schedule of these yet. That depends on what the engineers decide to do, but we'll have updates with that.
And you're good for
and
reconfig.
then the deployment of the full primary mirror as well. So
And you're
those
good to
things are
enable.
coming up later in the
Copy,
week.
go.
Just listening to what they're saying at the mock.
Mhm.
So seeing as we have a little bit of a pause for the Mission Operations Center, I'm going to wrap this up now because I think this is a wonderful chance to say thank you so much for everybody. Keith Parrish, thank you
Okay,
so
that
much for
prop
joining us,
completed
and for all of
successfully.
the
We're ready to
amazing
go with
explanations you've given us.
66.024.
And this is a historic day.
The
The
prop
first
looks
major
good.
phase of the commissioning, the deployment of the Sunshield is complete and successful, and I'm very excited.
That's
So
right.
thank you so much
Sunshield
for
team.
joining us.
And yep, thank you, Sunshield team, and go Webb, go.
Go Webb. Absolutely. Thank you for joining us. Please join us again later in the week. Goodbye.